Hello and welcome. Today we're going to be looking at the unit test for limits and continuity. I know that limits and continuity is usually the first topic of AP Calculus and it's a basic topic there, but we're going to explore it in the pre-cal version. This is going to help set the foundation for future studies in calculus, so it's extremely important that this topic is to help you in your calculus journey. With that, we're going to get started on our first question. Let's go. Function f is defined over the real numbers except for x equals 0. This table gives select values of f. What is a reasonable estimate for f of x as x approaches 0? Well, from both sides, we're approaching to 2.9, right? We're approaching to 2.9 from both sides, so our answer is going to be around 2.9. That's it. We can keep going. Trying to find the limit as x approaches 3 right here. All right, what are we thinking? Okay, so how is this going to work? Well, let's see. So we're dealing with these limits, and we're trying to figure out what does this function approach as we get close to 3. So I'm gonna pull out my calculator, and I'm gonna say 3 minus 10 to the negative 5. So I'm ending up with like 2.99999, like that. And now I'm gonna put that in for 3. So 2.999 minus 3, and then this thing times 4 plus 4, take the square root of that, and then we are going to subtract 4, and then we're going to do this negative 1e to the negative 5 thing over that, and we get roughly 2. Okay, 2 is what we get. Now we're going to have to do the same thing, but 3 plus 10 to the negative 5. We have to make sure it's from both sides, right? So 3 plus 10 to the negative 5, 3.00001. So minus 3, that's that. And then this times 4 plus 4 square root minus 4. And then you have, do this part again, and you get 2. So it's approaching 2, right? So that's our answer, and we can keep going. All right, this is the graph of the function g. It's like the x values at which g has a removable discontinuity. So it's something we can just remove, and the function is continuous. The only one like that is right here. Right, you take it out, and the function is continuous. If you take one of these out, still a jump discontinuity. Right? You're jumping up and down. So the only one is x to the negative 6, x equals negative 6. X equals negative 3 is a jump discontinuity, x equals 5. Well, that has nothing wrong with it, really. Like, that's completely fine. It's not going to be, like, differentiable, if you know what that means. That's a calculus topic. Don't really worry about it. But, at least not right now. But, that is completely fine. A sharp turn is fine, right? It's not like, it's still continuous there. So our answer is just x equals negative 6. And we can keep going. Which of the following functions are continuous at x equals negative 2? Well, if I put in x equals negative 2 into h of x, well, I can take the cube root of anything, even if it's negative, so that's good. H. If I put in f of x, I'm taking the fourth root of something that's negative, which is, it doesn't work, does it? So that's going to be undefined. So f of x does not work, h of x does, so my answer is A. Let's keep going. Find x approaches negative 1, this limit when you're given this kind of thing. All right, let's think about what we can do here. All right, so how are we going to do this? Well, what we can do is we can do the same thing that we did before, right? So negative 1, and then you're going to add 10 to the negative 5, negative 1 minus 10 to the negative 5, and you can plug this into anything, right? So 12 times like x plus 1, and then you can do that kind of thing. And you'll see that what you end up with for your limit is going to be, with the limit, right? If we just take this, plug it in everywhere, and we just keep doing it everywhere. Let's then we get that, again, that the limit is going to be roughly 6. Alright, that's what the limit is going to be. That's what it's going to go to. Alright, it's going to go to 6. Okay? So it's at 6. That's our limit. And we can keep going. Alright, so it wasn't 6. Let's think about why it's not 6. Alright, let's think about why it's not 6. Substituting x equals minus 1 results in this indeterminate form 0, 0. Well, we have this rational expression, and we can simplify it to this, right? That's something we should have done, right? We can simplify it by canceling things out on both sides. All right. Now, how do we proceed from there? Well, we know that if we just plug in negative 1, we get 12 over negative 2, which is going to be negative 6. All right, so negative 6 is our answer. And we can keep going. All right, let's keep going. Consider graphs A, B, and C. The dashed lines represent asymptotes. Which graphs agree with the statement? As x approaches 0 from the positive side, f of x approaches infinity. So here, we're at 0, and it's just like that, so no. Here, we're going to 0, and it's going to negative. Here, at 0, it's going positive. So that is our answer. And we can move on. Let h of x equals e to the 2x for x less than 0, and e to the 5x for x greater than or equal to 0. Well, at 0, e to the 2x or e to the 5x, just e to the 0, so it's going to be 1. So it's going to connect, so it's going to be continuous. So our answer is yes. Let's keep going. Function h defined over the real numbers except at x equals negative 7 gives select values for h. And we're trying to find the limit of h of x as x approaches negative 7 from the positive side. So that's from this side. So it looks like it's going really, 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 really small, but technically it's going big in the negative direction, right? So it's going really, really negative. So we think it's going to go unbounded. Right? It doesn't really seem like it's converging. It's going to go unbounded. It's going to go to negative infinity forever. And that's our answer. Let g be a continuous function on the closed interval negative 2, 4. A few values of g are given in this table. Which intervals must contain a solution to g of x equals negative 1? Well, how do we know that? Well, it's continuous, so you're going to have to hit that point somewhere if you have 2 points that are around it. So between negative 1 and negative 2, negative 1 is in there, so you're going to have to hit it somewhere. Between negative 2 and 0, there's going to be some point in there. Between negative 2 and 3, again, you're going back up there, you got to hit a point somewhere. And then 3 and negative 5, you're going back down, you got to hit it somewhere. All 3 of these intervals, it has to be something that has g of x equals negative 1. Let's keep going. Let g of x equals x over ln x minus 2. Select the correct description of the one-sided limits of g at x equals 3. So as x approaches 3 from the positive side, right, you have 3 over something that's the ln of something that's really, 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 like something that's really, really, really close to 1, but still positive. But still bigger than 1. So ln of that something is still going to be positive, except it's going to be really, really tiny. So you have 3 over something that's positive, really, really tiny. That's going to be positive infinity, so a or b. If you're approaching from the negative side, that's going to be something around 3 over something that's going to be less than 1. So it's going to be really, really, really tiny, but it's also going to be negative. So it's going to be 3 over something tiny that's negative. So that's going to be negative infinity. So our answer is B. And we can move on to the next question. Function h is defined for all real numbers. What is a reasonable estimate for limit of x as x approaches negative 2, h of x? Well, as we approach, we get somewhere like near negative 4, right? So negative 3.8, that seems like a reasonable estimate. Let's keep going. The limit as x approaches pi over 2 of secant x. Okay. So as we approach from the positive side, from the negative side, right? From what's less than pi over 2, well, the cosine is positive. So you're going secant, cosine is positive and really small. So secant is going positive and really big. And if you're from the negative side, from the positive side, as you go from bigger than pi over 2, then cosine is small and negative. So secant is small, is big and negative. So on one side, you have secant is big and positive, and the other side is big and negative. So it's not going to exist because it's on the opposite side of the spectrum. So the limit doesn't exist. Let's keep going. Find the limit as x approaches negative infinity. Okay, let's see what we can do here. So when we have this kind of approaches infinity kind of idea, what we do is we take the highest degree term from each one. So in the top, that's x to the eighth. So we're just going to do square root of x to the eighth. Right, screw that negative 5x cubed. Nobody cares about that negative 5x cubed. That's not the biggest degree term. We don't care. If we go to infinity, that negative 5x cubed is not going to mean a single thing. It doesn't mean anything. It's literally useless. Okay, so we don't need to care about that. The bottom, it's going to be 3x to the fourth. That's the biggest. So end up with x to the fourth over 3x to the fourth, or 1/4. 1/4. So as x approaches negative infinity, the limit is a fourth. So why was that incorrect? Right, let's think about why that was incorrect, why that didn't work. Right, so x is approaching a negative infinity. So let's clear this out. And so we're going to find the limit directly. So how are we going to do that? We're going to divide by both the numerator and denominator by the same quantity. That'll help us derive the limit. So we're going to divide by x to the fourth, or numerator by the square root of x to the eighth. That's the same idea as what we're doing right now. It's the same idea, right? That's what we're doing right now. Now, why didn't it work? Well, it didn't work because I typed it in wrong, right? Because this is going to be 1 and 3. So it's going to be 1/3, not 1/4. That is my fault, right? Now, functions f and h are graphed, right? As a side note, just make sure you write down the correct answer, right? Like, it's always helpful to go back and check once again so that you don't mess up the way I did. Okay. As x approaches -3, you're trying to find the limit of f of x plus h of x. Well, f of x doesn't really have a set thing, right? It could be either 3 or 0, whereas h is just 2. So, approaching from the left side, you get 3 and 2. That's going to be 5. If you approach from the right side, you get 0 and 2, which is going to be 2. So those are different. The limit doesn't exist. And we can move on to the next question. H and f, they're graphed. Limit of -1 as h of x over f of x. Okay, so h of x is going to be a -1. It's going to be 1. F of x, as it approaches, is going to be really, really, really small and positive. So it's going to be 2. It's going to be 1 over really, really small positive, which is going to be like infinity. So the limit's not going to exist. Limit doesn't exist. And we can keep going. All right. Wang Xiu Len. I'm sorry, I don't know how to pronounce that. But WXL, his teacher, or her teacher, I don't know, gave her a flowchart below and asked her to find the limit as x approaches -9 of g of x for g of x equals x plus 9 over -4x minus 6. So we're going to do direct substitution because, of course, we are. We put that in there. We get 0 over square root of 36. 6 minus 6 is 0. So we get direct substitution, as always. Always direct substitution first. We got 0 over 0. 0 is indeterminate form. That's D. All right. Trig factoring conjugates or trig identities. When you learn calculus, to learn about L'Hopital's rule. Extremely helpful. Remember it, but not now because we haven't gotten there yet. Right? So what are we going to do? We can try, can we do trig identities? We don't have trig. Conjugates, we could do a conjugate. We could try that. So if we did square root of 4x plus 6, then we'd end up with, on the bottom, we'd end up with -4x minus 36. And that would cancel out and give you -1/4 times the, so that would work. Conjugates would work. And then that'd give you just a big mess. But it would be a defined big mess. So it's a good big mess. And then we just do direct substitution. And then the limit's found. Right, we found the limit. And direct substitution, limit found. So we can check that, and we can keep going. All right. Here we are. H of x equals 1 over 2x for x is less than or equal to -2. 2 of x for -2x to 0. So at x equals -2, x approaches -2, we're going to plug this in. The first one is going to be -1/4. The second one is going to be 1/4. So limit doesn't exist because they're different on both sides. So you have a discontinuity, a jump discontinuity. Limit doesn't exist. That doesn't work. All right, let's keep going. Function h is graphed. Select all correct statements about h at x equals -1. So the limits on both sides exist, right? The limit does not exist because they don't agree. H is defined at x equals -1. Well, no, it's not. There's no filled in circle, so it doesn't exist there. So it's not continuous either. So the answer is A. And we can keep going. H of x is going to equal x minus 2 over square root of x plus 7 minus 3. H is continuous for all x is greater than -7. We're going to try to find h of 2. All right, so we plug that in, we get 0 over 0. What do we do now? We try to use some conjugates. So you're going to have x plus 7 plus x plus square root of x plus 7 plus 3. You're going to multiply that to both sides. And you can realize that for the bottom, it's going to give you x minus 2, which cancels out. And now you just have square root of x plus 7 plus 3 on the numerator. You plug in 2, you get 3 plus 3 is 6. Right? If you're a bit confused on all that, you can just write that down. Right? Multiply by the conjugate on both sides, and cancel stuff out and see what you get. All right, now we have the graph of function h. Which limit expressions agree with the graph? Choose all answers that apply. Limit as x approaches -4 as equals -2. So -4, where is the -4? -4 is here. Well, we can go from both sides. That doesn't really make any sense. As we approach 0 from the positive side, so this side, we get to 2. That's correct. As we approach 4 from the negative side, we're going here. We should approach 2, so that's also correct. And we can move on. All right, find the limit as x approaches pi over 2 of 3 cosine squared of x over 2 minus 2 sine x. All right, so here is where it kind of comes in handy to know your trig identities. Because there is a trig identity here in 2 minus 2 sine x. And the trig identity, if I'm not mistaken, is cosine squared of x. It's some variant of that. I think it's going to be 1/2 minus 1/2 sine of x equals cosine squared of x. So that means you're going to have 4 cosine squared of x, 3/4. That's our answer, right? It's that yeah, see, that's, you have to memorize those identities. You have to make sure you remember them. Right, see, it's 3. Right, I just put the magnitude the wrong way. It's going to be this 2 minus 2 sine theta, 2 sine x is going to equal the cosine squared of x, and your answer is going to be 3. Make sure you remember your identities so that you can do problems like this. All right, let's keep going. Consider graphs A, B, and C. The dashed lines represent asymptotes. Which graphs agree with this statement? Limit as x approaches infinity of g of x equals -2. As we approach infinity, so that's going to be all the way over here. We approach -2. That works. As we approach infinity, you get -2. Here, as you approach infinity, -2 also works. As you approach infinity, you get to -1. So no. So it's A and B. Let's keep going. Find the limit as x approaches infinity of 4x squared minus 3x over x cubed. Okay, so let's think about what we have in degrees here, right? So if we divide both of these by, say, x cubed, then you're going to end up with like 4 over x minus whatever, we don't really care because it's too small, over 1. And then this is going to become like literally nothing, because 4 over infinity is nothing. So it's just going to be 0 over 1, which is 0. Right? In general, if you have a higher degree in the denominator than the numerator, and you're going to infinity, you're at 0. And in general, also, if you have a higher degree in the numerator than the denominator, you're going to have an infinity or negative infinity. That's what it's going to be like. If they're the same degree, that's when things get interesting and you have to actually do stuff. But otherwise, not that difficult. Functions f and g are graphed, and we're trying to find limit x equals 2 of f of g of x. Sorry, g of x as x approaches 2. It doesn't exist, does it? Right, as x approaches 2, well, it goes down to negative infinity and up to infinity, so it doesn't exist. Limit doesn't exist. Let's keep going. All right, so we're going to let f of x equals the cube root of cosine times pi times x, cosine of pi times x. Below is Isaac's attempts to write a formal justification for the fact that the equation f of x equals 0.1 has a solution where 1.5 is less than or equal to x less than or equal to 2. Isaac's justification, f equals 1.5 equals 0, f of 2 is 1, so there has to be something at 1.1 in between. Well, that seems like it's good, But he didn't mention that the function's continuous, right? This only works if it's continuous. If it's not continuous, you could be like whoop and then whoop, and you could skip anything in the middle. He didn't say it was continuous. He didn't establish that it was continuous. That was his issue, and that's our answer. Let's keep going. Function h is defined over the real numbers, gives a few values of h. What is a reasonable estimate for the limit as x approaches -6? We're going, as you can see, to -1. Our answer is -1, and we can keep going. Find limit as x approaches 5 of x plus 2 over x squared minus 5. You plug in the numbers. You get 7 in the numerator, you get 20 in the denominator. So 7 over 20. That's your answer. Let's keep going. This is the graph of the function g. On which intervals is g continuous? Okay, so from -2 to 0. Well, because this is not defined at 0, so that's not continuous. From 1 to 5, well, you have this issue right here where it's not continuous. So neither of those are continuous, so none of the above is our answer. And we can move on. We want to find the limit as x approaches 0 of x over sine of x. Direct substitution and other algebraic methods don't seem to work. Looking at the graph, f of x equals x over sine x, we can estimate that the limit is equal to 1. To prove it, we have to use the Squeeze Theorem, which honestly, it's a pretty fun theorem. Alright, and each suggests that we use these two functions in order to apply the Squeeze Theorem. Does each suggestion seem to be correct? Looking at that, if you don't know the Squeeze Theorem, it might look correct, but it's actually not correct. Because the idea of the Squeeze Theorem is that you squeeze a function in between two other functions. I don't know why this cursor's not working. Okay. Anyway, so if you're using the Squeeze Theorem, one function has to be going above f. The other function has to be going below f the whole time. H and G go up below f and above f at different times, and that messes everything up, right? So you have to have, because it's not true the input of one function is always below and the output of the other function is always above it. Yeah, that's what we mean. Near 0, near this value, the output of one function is always above, the output of the other function is always below. You squeeze it, right, in between. You can't have it like a sandwich, right? Like if you're considering f as like the whatever's inside, and then the bread as the other two, or you have to squeeze it in between. If your bread is sideways or something, and it's like it's intersecting each other, you can't make a sandwich like that. It's not a sandwich. That's just some screwed up thing that somebody thought of. Right, and that's our answer. Let's keep going. Given the function g and asked to estimate limit as x approaches 4 of g of x, 3 students created tables. Each table is accurate, but which one is best for approximating the limit? Well, we want to approach 4, and we want to approach it from both sides. C only approaches it from one side. B approaches -4 and 4, so no. A approaches it from one side and the other side, going really, really close, 3.999, 4.001. That is correct. That is our correct answer right there. Alright, so that was this topic on limits and continuity, one of the most basic and most foundational topics in calculus. It's very necessary to learn when you're going through calculus. I hope that this video helped you in solidifying your pre-calculus knowledge and getting ready to move into calculus. This is the last topic in pre-calculus. Sometimes it doesn't get taught, which is a shame, but it is a very important topic for calculus. I hope you liked this video. I hope you enjoyed it. If you did, please be sure to like and subscribe. And with that, I'll see you next. I'm going to continue looking at more topics in math in general. I'll see you then.